I just want to continue now with our first topic and to provide you with a short introduction to CANopen FD. Yeah, why CANopen FD? Why do we need this? As I've already introduced, CAN-FD had been developed, it had been presented in 2012 on the International CAN Conference organized by CAN and Automation. And we have now a data link layer, the CAN-FD data link layer that is capable to provide a higher data throughput. And of course, we can run on this data link layer a classic CANopen stack. And if you have already done some researches or you will find some papers, already in this setup, you can gain from CAN-FD. But a CANopen FD stack is limited to an 8-byte payload. So this means if you want to make use of the full impact of CAN-FD, of the full functionality that is provided by CAN-FD, then you need also a protocol stack that is adapted to this data link layer that is capable to run CAN-FD frames. And this evaluation, how can we achieve such an updated data link layer protocol, run in the interest group CANopen FD. And as a result, this interest group CANopen FD released in 2017 the CANopen FD specification, CIA 1301. So if you want to know what's going on in CANopen FD, how is it specified, then please go to CAN Automation's website, download this document, and you can learn what is CANopen FD about. First, CANopen FD protocol stacks have been available since 2018, and first devices been exhibited in 2019. So what is a CANopen FD device? So when the working group was started, the working group said, we don't want to reinvent the wheel. We want to take a lot of the things that we have already learned, that we are familiar with, and that had proven itself from the well-existing CANopen. So it shall not be a total shift, but we have to see where do we have in CANopen some limits, where do we have some advantages in CAN-FD that we want to take over in CANopen FD, and there maybe we have to break some rules that we are well known from CANopen, from classic CANopen, and therefore we will see, okay, let's start with a device model. How does a device model look like, and does it differ very much from existing CANopen? And we see here a simplified class diagram of a field device hosting a CANopen FD device. And we see here, okay, we have here our, let's say, based on a microcontroller, a device that's the microcontroller supporting a CAN-FD controller. And here I have to initialize my bitrate in classical CAN and CANopen. This would be one nominal bitrate. Now you have to think about that you have to handle two bitrates, a nominal bitrate, and in case of doubt, in case you want to use the increased data throughput, then also another bitrate that is used in the data phase to increase data throughput. Then we have our CANopen device running on this CAN-FD controller, and we have to deal with our node ID. And furthermore, there's another identification. It's the network ID. We have now two identification numbers. We have a node ID and we have a network ID. And all the rest looks rather similar to that what we know from a CANopen device, from a classic CANopen device. There's just one additional amendment. We care here also about, let's say, network management managers. So we are using here since some months, we have decided to use inclusive languages. So we try to substitute master, slave by server and manager. So you see here in this network management manager functionality in classic CANopen, this was handled by amendments. Now we have it in the basic CANopen FD device functionality already integrated to care about the distinguishing between a server functionality and a manager functionality. All the rest was kept stable. Just for reminding us, CAN-FD, what was this? What was the major impact? The major impact was that we have here an extended data field, what we want to use. And if we want to increase the data throughput further, we can transmit this data field, this extended data field, in a faster way with a data bitrate. So we have, if we like, 2 bit rates, and we have, if we like, an extended data field. So these are the key elements we can play with and we can use to increase our embedded network functionalities. And we, from a CANopen FD perspective, we have to care about this. So we specified default bit rates, so pairs of nominal bitrate and data bitrate. During the introduction of Canon Automation, I said Canon Automation in its working groups has the objective to simplify network integration of devices. And this means the users should not struggle around too much with bitrate settings and these things. These are predefined now already. Combinations of nominal bitrate, data bitrate are predefined in the specification. You can just adjust predetermined pairs of bit rates, and then you should be interoperable with the other devices if they choose the same pair of bit rates. Nevertheless, this CANopen FD specification had been written more or less by software guys, not by the CAN FD physical layer experts that are also available in Canon Automation. But we said, okay, we don't have to be more clever than those. So people who are dealing all the day with physical layer issues in CAN-based networks, so just rely on the results they have already created. Therefore, we are pointing more or less on the specification series 600 that is available at Canon Automation Office. And you see here, we have a broad set of specifications in this context. And you can just go to them and can see what about physical layer implementation, system design implementation, signal improvement, and so on. We have there also a lot of presentations out there. You can learn from them, or you can also go to Canon Automation website and to the ICC presentations. So also here, a lot of physical layer issues have been presented. And I think it's a lot of valuable content if you want to learn. So it's no need that we repeat these things in the CANopen FD specification. What is once again in the CANopen FD specification, as I said, the introduction of network ID and node ID. You have to be aware that you have to set in a CANopen FD device both attributes to learn your device, in which network are you present, and what is your node identifier in this network. How you adjust this CANopen FD does not care, as CANopen did not care. There exist several solutions. In the CANopen environment, I would say more and more applications like to use the layer setting services. And as this is a fact for CANopen FD, we have already updated the specification 1305. It's now an updated type of the layer setting services with special regard to usage of layer setting services in a CANopen FD environment. More details on this you will also find in a very nice presentation from my colleague Ms. Yao from the International CAN Conference. Furthermore, also here Emotas on this occasion showed some additional flavor of assigning node ID and node ID negotiation. So we are considering currently also to introduce this in the CANopen FD environment. Moving one step higher with regard to CANopen FD, dealing with the application layer, we see CANopen FD introduces also a network management finite state automaton. It's more or less identical to that what you know from classic CANopen. The only difference is that we are clarifying very in detail where is a node ID value applied, when is the node ID value visible at the communication interface of your CANopen device. And another difference is that we consider formerly known master, now manager finite state automatons. When does the manager functionality and which share of manager functionality begin, when it is started? All the rest is completely identical to that, what you know from classic CANopen. Then you see here the services. We have analyzed which services need an update. As I said, as many CANopen functionality that we could keep stable, we kept stable. Only those services and functions that would really benefit from the usage of CANFD and where a change makes a major benefit or provides a major benefit, they were changed. All the rest was kept stable, so that you are enabled to reuse a lot of your classic CANopen knowledge. And we see here, most of the network management oriented services, they were kept stable. The synchronization protocol, the timestamp protocol, NMT protocol, boot up heartbeat, everything remained identical to that what you know from classic CANopen. What we enhanced and changed was the emergency protocol. You have now some additional, more detailed information about the error event. We updated, of course, the services for the data transport, the process data object, as well as the service data object. You see also the name change to universal service data object, because these 2 or 3 services, they are really limited by the classic CAN message, and therefore it makes really sense if we have now a CANFD data link layer that we update these services to make use of the entire payload of the up to 64 byte provided by our CANFD message. Let's have a brief look on these protocols. Emergency, we see here the emergency message is enhanced to up to 20 byte. So that we see here, if you are a little bit familiar with CANopen, you will find your old CANopen emergency message with the emergency error code, the error register, and some manufacturer device specific information. And this is now enriched by a timestamp that you can bring the error events in the correct chronological order. You get some additional information about the error status. And if you have more complex devices, you get the information which share of the device is now in some troubles, where in my device resides this error event. We have also some complex error history that allows you to store all the errors that came up during system runtime. I know typically in your systems there are no errors, but if there may be devices in your system from a third party, then there may occur some error events. And here we have an error history domain, and to control this domain and the type of error recording, there's also a parameter now introduced, the parameter 1031. And this allows you, on the one hand, to adjust how to record the errors, which error events shall be recorded or removed, and to treat this entire error event. For a fast look, which kind of errors are really at the moment in my system applying, then we have also this active error list. This is just filled up and displays only the currently active errors. All former errors are removed. So you see with a very quick look what's currently going on in my device. As I've said, for data transport, we have PDO, SDO. We in CANopen FD, we improved here the PDOs that we have up to 64 byte payload. All the rest was kept stable. So this means we have to modify our threshold value. In classic CANopen, we can fill up to 8 byte. Now we can fill up to 64 byte. All the way, we define a PDO with communication parameters, mapping parameters was kept stable. The only thing that we have to consider, in addition to the threshold of filling up PDO, is that CANFD messages cannot be extended according to the required payload, but only to the next supported frame length. So therefore, I depicted here the way you can extend CANFD frames in given steps. Only these frame lengths are supported by CANFD. So if you want, for example, to transmit 17 byte, you have at least to transmit 20 byte. You have to consider some padding bytes. Well, we can now fill up to 64 byte in one PDO. With regard to applications, maybe it's good to know You can rethink the way you control your applications up to 64 bytes. This allows you, for example, if you have a drive control application, you can control via one PDO several drives with one single command. This may ease your strategies to control all the drives in a rather synchronous way. And we considered this already in an updated document, CIA 402-6 for drive control. With regard to service data objects, there had been also some considerations how to update the classic SDO, but it was rather difficult as we hadn't had any not used or any unused command specifiers to identify now another flavor of SDO communication. Anyway, as CANFD and classical CAN are not really interoperable or compatible, we had to do a switch and a real cut on this point. And therefore, there was a consideration, maybe it is worthwhile to overcome some limits classic SDO communication has. So we know that we can describe in CANopen fully meshed systems meshed with SDO communication where every device is to every other device an SDO channel. But in fact, only a minority of devices does really support SDO client functionality, additional SDO servers in addition to the default SDO server. We do not have SDO in broadcast. It's always a one-to-one session, one client with one server. And so there exist some typical limits in some applications. And therefore, when we introduce now an updated SDO, why not taking the chance and overcoming some of these limits? And exactly this was what we did in the IT CANopen FD. So we introduced an updated SDO, and very new SDO. It's a Universal Service Data Object, or briefly the USDO, where a sender determines the CAN identifier of the used frame, and this allows us to say, okay, the destination where this frame is going to, this is coded in the frame itself, and this allows us on the fly establishing dynamic communication channels between one or several devices in the well-known style, expedited, segmented, or bulk transfer. We allow parallel accesses. We introduced an inherent routing capability. And for error handling, we provided detailed abort codes. So one of the major changes is that not the server determines anymore the CAN identifier, but always the sender of one of these frames, and the destination, as I said, is coded here in the data field. And therefore, I can establish all the communication techniques that we, coherences that I've already presented. I can have one-to-one sessions, unicast, multicast, or broadcast communication. You see here the coding, it's more byte-oriented, should be more easier to implement. And we code in the first byte, what is the destination of this frame, which communication style do we have, unicast, broadcast, multicast. Then we have the command specifier. The command specifier gives us the information, which kind of SDO transfer do we using? Is it expedited, segmented, or bulk transfer? And if it's expedited, we have the data directly here in the initiation frame of this USDO transfer. In addition to this, to the data, we have a description of the data according to data type and size, where, if it's a write access in the object dictionary of the server, do we like to write, index, subindex, well known from classic CANopen. And in addition to classic CANopen, we have here a kind of transaction number, the session ID, that allows us having several transactions with the same or different devices in a system. So you see here segmented transfer that allows us, after a short preamble, that we have here our data up to 60 bytes per segment. We can have here application data, what allows us in one segment to accelerate much in comparison to classic CANopen, where it's just able to provide 7 bytes per application data per segment. And if we like to accelerate further, we have here the bulk transfer. Bulk transfer has here a very short preamble, just negotiating, yes, can we use this bulk transfer, informing a little bit about timing constraints, what are appropriate timeframes for getting the data, for processing the data and receiving the next one. And if this is negotiated, then we can go ahead and send one frame after the other and one share of the data after the other, which can accelerate data download much. But just giving you some ideas, how can I benefit from this? Or in which use cases? One major use case is, of course, download of configuration data of firmware and so on. Or, for example, end-of-line production, if you have several devices that need the same configuration, you can really benefit much. I did for some other conferences some calculations, and I was calculating roughly if you take 16 kilobyte of firmware with classic SDO in a segmented way, you need roughly 9,300 CAN frames, and as every CAN frame is confirmed in an classic SDO, you can double the number of frames, and they are all of the same size because a classic CANopen SDO is always formatted to 8 byte. If we do this with the segmented CANopen FD USDO service, then we scale down the number of frames to 1,200. Of course, it's longer, but even if we avoid the bitrate switching, just by taking the service, we can do this firmware download in roughly half of the time. Not considering that we can even add now a bitrate switching, not considering that in classic CANopen, if we have a second, a third device, we will have the same time twice or a third time. In CANopen FD with the USDO supporting broadcast mechanisms, we can do download of the very same firmware to the same devices at once, so no additional time is added here. So we can benefit much. Also, the ability to dynamically establish cross communication allows us to support requirements that we have in modern networking. I would say it's more and more in more and more applications, it is a requirement that the end user is adding some modules, removing some modules. Think about Pedelec, where you change the battery or add some new functionality. Then on the fly, you need to establish communication channels between a host controller and these devices. And all this is very simply done via the USDO, which can dynamically start cross communication between all the devices in the network. So finally, with regard to the SDO, I want to emphasize that the USDO provides inherent routing capability. So we have always two possibilities to communicate with the USDO. You see here the local command, and here you see the very same command in a long distance routing style, where you provide the destination network and the destination node ID and the source addressing. And just by swapping both, all the devices know where to communicate and where shall we route the data and where shall we route the answer. And sometimes it's also a question, what about migration paths? Due to lack of time, I don't say too much about migration paths, just that we have already discussed. There exist also some presentations on migration paths from classic CANopen to CANopen FD, and I think also in one of our next IG CANopen FD meetings, we will have this topic once again, just for finalizing what is new to CANopen FD in comparison to CANopen. You see here some updated parameters. One of the major changes is the object 1000, which is now available as an array, listing also supported virtual devices, or let's say implemented device profiles. You have now a further entry for versioning. You have these error histories, and you'll be caring about NMT manager master application. Yeah, what's new furthermore is the decision that CANopen FD devices have to be tested. So in contrast to classic CANopen, if you want to call your device a CANopen FD device, it has to be conformance tested, and we are here at CAN Automation enabled in the meantime to test your devices and to approve them and give them the label, yes, it's a CANopen FD device. To enable automated tools to run CANopen FD, we have already cared about an electronic device description. I keep short here because my colleague Mr. Kaplun will say some words to this. I just want to give you the information that this is already available. And there is a good wording, availability. So it's not just paperwork CANopen FD. Protocol stacks are available from several companies, EMSA, Emotas, ESD, Microcontrol. I/O modules are available and have been displayed already on the fairs. And also with regard to migration passes, CANopen FD gateways are under development. So, small summarization. CANopen FD, the basic CANopen functionality remained unchanged. We have now support of 64-byte PDOs. So also with regard to applications, you can think for condition monitoring, enhanced security solutions, and so on. This can be rather beneficial. Don't underestimate the big variety of possibilities provided by the USDO. And also the emergency brings you maybe much support in doing some diagnostics on CANopen FD networks. Yeah, furthermore, you have seen the history of CANopen has not been written yet. We're still working on CANopen. With CANopen FD, we have now the next generation. The work on some enhancements is not or has not been finalized yet. And this will then be presented by my colleague, Mr. Kaplun. Furthermore, some details on CANopen FD are provided in the ICC, which is recorded and available by videos. So much.